is figuring out the 3 decimals. So come as close as you can. And if something's only going 5 seconds in the air, you can make your T-step be very small. That'll help you narrow it down a little bit better. Because 4 seconds isn't going to take that long to do. If it takes 60 seconds, that's going to take you a little longer if you make your T-step too slow. Because that's the parameter that's going this way. This is the nice part about applications. You can't really see that time, but that's when you use the third parameter. And when we make a rectangular grid, we're just plotting our x and y. So we can only plot those two things. When we make this graph, we only can put x and y on here. We can't see time go like this. But our third parameter gives us that time. So way back in my day, when I took physics, we used to call them snapshots. Like, take a snapshot. Where are you now? Like, where are you after 4 hours? So we would figure out where this rocket is after 4 hours, the angle that it turned, the speed that it's going. So we just, I don't know what you call them now, but years ago, we called them snapshots.
When I still have full credit like real math, it got equals 3.75. It got like 977.
Yeah. That's fine. Within reason, like if you gave me 0.962, that would be off. But if you're within reason, that's fine. They're a little bit more exact doing this, but and play with it. Your exactness is going to come off your table, not from your trace. So go to your table when you get close enough to something. Set it to 0.001 so that you get your 3 decimals worth. And also remember, sometimes they can't round. So you got to scroll to that number to see where the rounding is. Probably a lot of this is a little bit more tedious work. Any other questions on this? No? So here's where we subtract it. Because when she goes this way, and you take a shot of this, you went from here to here. So this was 26.701. So you want the distance here. So just subtract that from 78, whichever one you called Chris, whatever one you called Linda. And she can't be more than 78, because she doesn't reach the other girl. Okay, the NFL guy. Where is it? I think mine are backwards. I think 5 comes over here. Okay. I did it a couple of different ways. An NFL punter at the 15-yard line kicks a football downfield with an initial velocity of 85 feet per second and an angle of elevation of 56 degrees. So when this guy kicks, he's already at the 15-yard line, right? How many yards is in the football field? 100. Okay. So he's already that. Now, how far downfield will the football first hit the field? It depends what you looked at, how far downfield. So I think I did it both ways. How far downfield, what yard line does it land at? Or how far downfield, what distance did it go? How did you look at it? Did you look at, like, he's at the 15-yard line. How far did he kick it? Or did you look at what yard line did it land on? How far did he kick it? So if you did how far he kicked it, or if you did what yard line he's on, you're going to get 2 different answers because of the 15. So I think I remember doing this both ways. I did it both ways here. You added 45. Okay, you got to go to feet. You got to go to feet. Be careful. Yes, be careful. He's at the 15-yard line, but your velocity is in feet per second. So if you want to add the 15 yards, you got to add it in feet. So I did this both ways, depending on which way you looked at it. I kind of looked at it this way. Adding the 15 feet, this is going to tell you like where on the yard lines it actually lands, but this is how far he actually kicked it. So whichever one you looked at, I think they meant this one, like what yard line did they land at. Hang time, your hang time is just the time in the air. So if your parabola goes from here to here, that's just the time from there to there till it hit the ground. Let's just say, when did it hit the ground? How long before your ball hit the ground? That's what your hang time is. So whichever set of equations you used, this one or this one, just follow like the answer for that. Your answers will be, your hang time will be the same, but your distance down the field will just be different. This is how far he ended up kicking it. This is what yard line it ended up on. I think it's the opposite. This is where it landed on the field. This is how far he kicked it, because we started at the 15. How did I calculate? Because I calculated it from the 0. Like, your football field is like this. So then you got to start it here. Started at the 15. Well, in feet, 45. 15 yards is 45 feet.
So was the red one like the right way you did it?
Either one, whichever way you interpreted it. It depends how you interpret it. This far down the field, I originally just did this. I did this. I thought it meant what yard line did it land on. And then over the years, when we do this together, someone said, well, I interpreted it as how far did it go. So either way.
Wait, what's the 254? That's how far it went.
That's how far it went. Feet, and then you're going to convert to yards.
Then why do you have 200? Oh, okay, never mind.
It depends which way. The only difference is that 15 yards, 45 feet.
I know it's downfield.
Downfield, like, where did it go downfield? I interpreted it as how far downfield, what yard line were you at?
I was going to Google it, but then I don't.
But how far downfield could also be how long was your field goal kick? How long was your kick? Because in football, that's what they do. They tell you you have a 45-yard kick. They don't say, oh, you landed on the 60-yard line, you have a 60-yard kick.
Wait, now I'm even more confused. If you're at the 15-yard line, it's really not necessary to go back. Okay, I just don't understand.
No, it is important to like get it
If
good.
you're on the 15-yard line, then there's 85 yards left on the field.
Oh, so they're kicking that way.
Yeah.
So you're kicking the long way? I
Yeah.
said that in the beginning.
Absolutely.
Yeah, I'll just kick it.
I didn't want to too close to your goal.
Wait,
Yeah.
I thought once you add a 45 in the original equation that you don't have to subtract. Because you're already starting at 6.
Then, this is your distance traveled. So you started at the, because you started at the 45. So where did it land? And then subtract where you started from, I guess, because you're starting there. Does this make sense? I know, I did it originally that way. And then one of my students said they interpreted it this way. Hang time, how much time in the air? That's just the distance from here to here. Wherever you start, wherever you stop, that's your time. So wherever you start this thing, when does this hit the ground? How long did that take to hit the ground? And again, when you kick a ball, throw a ball, bat a ball, golf a ball, it's in seconds. Your seconds. Don't make that T-step be too large. Because then you're going to get like something that's going to go like this. It's not even going to look like a curve. So just kind of play with these things.
I asked 15, but I got like the same answers.
All right, so what did we solve? We solved for T. We said T was x minus 7 divided by 2, right? So you're going to plug this into here. But what I want to do first is this. I want to, my calculator, that's over here. I'm in parametric mode. I just want to graph my first one. So I want to put this in. I want to see what this is going to look like. Get rid of everything else. Remember they're pairs, so just be careful if you erase something, make sure you start back at an x. So 2t plus 7. And 2t squared plus 2. And you might have to change your window a little bit. I just do it in 6. Oh, I'm not having it. So I've got some kind of parabola. Can I tell what my vertex is? Kinda, sorta. So I can kind of estimate, maybe it's like 7, 3, somewhere over there. When I get my equation of a parabola, I kind of should be able to see that it looks like this. So substitute this in. Okay, you have got to square this. Excuse me. You have got to square this guy first before you take out the 2. So, and already I can see, oh yeah, what's my vertex part? 7. Because you can kind of see it, right? Now I can take out this 2. You square this guy first, then you just reduce this. And actually, I'm just going to make it into vertex form. So I'm just going to pull the 1/2 out. Can I see my vertex is 7, 2? Am I opening up? Is your parabola opening up? It's positive, right? And this is just a transformation. It just made me a little wider. Does my parabola look a little wider than my normal parabola? A little wider. Does it look like it's at 7, 2? Yeah. Well, it's going to end up like coming out like that. It's going to come out like that. Come on, this is just algebra. You got to be able to do this. You got to square first. So square the top, square the bottom. And then don't even just pull it off to the side then. Just do 2/4. That reduces to 1/2. Because this kind of doesn't really help me when I look at this. But I know my parabola has a 4p in front of it. I don't care what my p is right now. But I know it has that number in front of it. For my transformations, that tells me am I wider, am I narrower? If it's negative, am I reflected? Where am I going up, down?
You have to solve like in terms of x, right?
So your final answer has to be this. This is called the rectangular equation. Why? Because it's using an x and a y variable. An x and a y variable. I can't put my parameter on my regular plane.
If you left it as a 1, like right
Before it, yeah,
okay as well.
that's fine. Yeah. We generally pull it out in front because that's where we see your transformation, but I'm not that far. I'm not that particular.
So like the next one you'd have like a big radical, right? You know? Like when you saw me do x plus this, then the 8 square root that whole thing.
Yeah.
So then you put the entire thing.
Yeah. And are you squaring it here? No, you just leave it.
Yeah, so
And well, when you graph this, you should be able to see what you're getting because you're putting this one into that one. So my advice is graph it first. Graph it first so that it's not so scary looking. So when you graph this guy, is that a minus? Minus 6. Is that another minus? Minus 3. Okay. When you graph this, it's a sideways parabola. Sideways parabola is a y squared, isn't it? So if something has a square root, how do you get rid of a square root? You square it. So isn't that going to force your y to become squared? I think this will help you more because if you substitute this in and you just leave it like this, and then this thing has your radical,
yeah.
does that really mean anything to me? Not really. So what if I move this 3 over here? So I'm going to move the 3 over and isolate my radical, right? Because we always know you isolate your radical before you square it. whatever this thing happens to be. Now I'm going to square both sides. Doesn't this look like a y squared parabola with a vertex? So am I kind of at the -3? Am I kind of down here? Am I kind of down here at the -3? Yeah. And regardless of what my x comes out to be? Yes. So you're going to square both sides.
So did you have to divide by 6 to not?
You can divide by 6 first if you like, and then square both sides, but I would square both sides first.
I thought you couldn't square it.
Your radical is isolated, it is by itself. It just can't have another term there. Like, don't square this, because then you're going to end up with another radical. Just get this term over here. You can keep the 6 there or move it later. That part doesn't matter. And I'd leave it there because that's what your parabola looks like, isn't it? If your y is here, isn't that where your 4p goes?
You got that,